All right, I'm going to do two gas laws now, Charles' law and Gay-Lussac's law. So let's start with Charles' law here. In Charles' law, as you can see, as you increase the volume, we're going down here, sorry about the messed up arrow, but as you increase the volume, your temperature is also increasing. So what that tells us, if we have a direct relationship, you can see as volume increases, so does temperature. So we can use this equation right here to solve for one variable if we're given the other three. Again, we have one showing you that that is the situation conditions that happen first, and then two, that would be second. So you'll see here in a second that that kind of goes, two sets of data go together just by understanding the question. Now with this one, we are going to use a temperature of Kelvin. So if you're given a temperature in Celsius, you need to change that to Kelvin. And that's something we talked about already. And it is also assumed that when you're talking Charles' law, you're also looking at a situation where the mass is constant and so is the pressure. So let's go ahead and look at a problem here about Charles' law. So as you can see, we have the equation right here, and we have some numbers up here. Again, we're going to put 3, and you can see that these two are sort of together, which implies they happen first. So these are our 1s. So again, this would be 473, and again, our units are nice to keep track of here, but it kind of makes sense in the end. Now, 36 degrees is what we have, but that's in Celsius. Remember, we don't want that in Celsius, so we just add 273 to that, and we get a number of 309. A little messy, but works. We want to know the volume, okay, so there's our question mark, and then our temperature, again, go 94 plus 273, and that will equal 367. All right, so then we're going to take this equation right here, and we're going to put 473 in the top, so that takes care of that. We're going to put our temperature, which is 309, right here, not 36. And we don't know what V2 is, so we'll put that and leave that. And then we'll put 367 right here. So we've put all these variables in. So then we'll simply do we do two things. We can cross multiply, taking 473 times 367 and divide by 309, or we could simply solve for V2. Either way works by multiplying both sides. But your answer should be, when it's all said and done, V2 equals 562. And again, that is in milliliters because we were given milliliters right there. So 562. Again, I have, with this, I'm going to use 3 sig figs because I have 3 sig figs here. I have 3 sig figs in the 309, and I have 3 sig figs in the 367. Even though these were given as 2 sig figs, I'm always assuming it's going to be in Kelvin. So that's how we do Charles' law. Very similarly, we look at Gay-Lussac's law, and again, as the temperature goes up, and this is simply a relationship between temperature and pressure. As the temperature increases, the pressure is also going to increase. So think about if you had a, let's say, a balloon that you blew up on a winter day, and inside where your house is warm, that balloon would be whatever you filled it with. It'd be a nice filled up balloon. And then say you take it outside, and you take it outside and it's in your car, it would actually shrink. Same as like a basketball. If a basketball is in the garage all winter, or any sort of ball, it'll kind of shrink down. And then when spring comes and summer, it might actually expand back out because the temperature increases. So as you can see, as the pressure increases, so does the temperature. So this is a direct correlation, direct relationship. We can use a very similar equation for this, and again, we're going to have to use Kelvin, not Celsius, and this is at a constant. We're assuming everything's constant as far as mass and volume goes. So if we look at the example here, and as you notice, even though we prefer atmospheres, we can use torrs. That's no problem. So as you can see here, we got 765 and 23. These are together, And so these are going to be our 1s, meaning our 1s over here, down here. So we'll put 765 right here as TORs. We'll take 23. Of course, 23 has to have 273 added to it, and that'll be 296. P2 is right here, and that's 560. And then our T2 is a question mark. Now the nice thing about this T2, it's going to spit out the equation as Kelvin. And the reason it is because 296 right here is Kelvin. So you don't have to convert it again. It's already converted for you because of the relationships that are going on here. So we put 765 up here for P1. Our T1 would be 296. And that's going to equal 560 torr divided by T2. We don't know what T2 is, but we do know it's going to be Kelvin. We can do a cross multiplication here, and the answer we get is 216.679, I think. Whoops, that's kind of crazy. And that's what spits out on your calculator, but that's not what we want, of course. We want to look at the fact that we were given 3 sig figs. So again, 3 sig figs, 3 sig figs, and this is 3 sig figs because of that point right there. So we'll round 1, 2, 3. We'll look at the neighbor, and our neighbor tells us to stay or go. In this case, it would actually tell us to go up because of the 6, and we would have to label this as Kelvin. So anyway, that's 2 more gas laws. Nothing too groundbreaking here. Both of these gas laws are going to show a relationship that when one variable goes up, the other one also goes up. It increases. So pretty similar, and work on those problems that are on Canvas and get your answers. Don't forget to put your answers around your answers using sig figs, of course.